Alright, this is AQA AS Level Physics 2024 Paper 2. That is Practical Skills and Multiple Choice. As per usual, unlike OCR and Edexcel, AQA don't allow me to put the paper on screen, otherwise they will copy strike the channel into the abyss like they almost did in the past. But they do allow the questions to appear on websites like PMT, so figure that one out. So make sure you get a paper and mark scheme to follow along. The links are in the description. We have a hacksaw blade. So we have measurements of 60t. We're asked to find the mean value, so we're just going to add all these up. And just be careful when you are asked to calculate an average or a mean, then just be aware that they might throw in an anomaly. It doesn't look like we have one here. And you know what? We're going to be dividing by 4 because it's the mean, and then we're going to be dividing by 60 again. So let's do both at the same time. Why not? So let's just divide it by 240. And again, just be careful that when you write your answer for the mean, it cannot be to a greater accuracy than the data you used. That means we can't go to more than 4 sig figs. So I think that gives us 0.418 seconds. No anomalies there, so didn't have to omit any from the calculation. Okay, now what? Oh, so it's wiggling around. Oh, it's like a seismograph. 2 whole pages of information. That's a joy. Okay, so now we have this graph. Oh, 3 whole pages of information. You are spoiling us, AQA. Right, so we have the time period. So I guess we're just going to do... What? How many oscillations is that? Starting at the bottom. So how many oscillations? So we're starting at the bottom and then we go 1, 2... But then it's stopping there, so it's not going to the bottom again. So it looks like we have 1, 2, 2 3/4 oscillations. So 2.75 oscillations. And so multiply that by our time period. So we end up with 1.1, 3 sig figs. Let's go with that. So 1.15 seconds. Cool, so we have the time it takes, and now we're being asked how far does it go? Okay, so we're going to have to use the scale. I'm going to use little squares, so I'm going to say little boxes, little boxes, little boxes, little boxes. So I'm going to go from the bottom. So 1, 2, 3, I'm just going to skip. 17 boxes, there we go. And that's times by 10 millimeters each, because I split that big box in half to make it easier for myself, I guess. Yeah, that's right, because they started halfway up a big box. Oh, that's such a year 7 thing to do. And so, well, we need that in meters, so I'm going to say that's times by 0.01 meters. So that gives us 0.17 meters. Okay, so we have a time and we have a distance. So, of course, we're being asked to calculate acceleration. So we're going to use SUVAT. So that starts off at 0 meters per second, of course. V we don't care about, we're looking for A. So we're going to use S equals UT plus half AT squared. As per usual, UT disappears. So acceleration is equal to 2S divided by T squared. So that's 2 times 0.17 divided by 1.15 squared. And that gives us 0.2... How many sig figs are we going to go to? That's the 2 sig figs. So paper 2 especially, and then paper 3 at A level. Be careful with the practical skills. Try and go to the right number of sig figs, especially in these parts of the papers. So I'm going to say 0.26 meters per second squared. All right, 1.5, bit of uncertainties. A teacher suggests that the uncertainty in S is plus or minus 2 mil. Explain why this is a valid suggestion. Well, that is because, they've gone with my interpretation of uncertainties. Each line on graph paper represents, or is, not even represents, but whatever. Let's put represents. Basically, they're 2 mil apart, that's the point. So therefore, that is the resolution of the graph paper. And again, people get their knickers in a twist about this one. Is the uncertainty the resolution? Is it half the resolution? Well, in this case, I mean, the thing is that you could say, this is what they want you to say, if the uncertainty is half the resolution, which I don't think it is, but whatever, we'll go with it. I think it's the resolution. Total uncertainty is equal to 2 times the uncertainty due to making measurement at start and end. Again, I don't think that's true because it's not like you're measuring at the start, you're just lining it up at the start. That's not the same as making a judgment call. And so, as per usual, the very nature of uncertainties and all this nonsense is ambiguous. Okay, so we're talking plus or minus 0.46% in TQ. Determine the percentage uncertainty in your result for A. Okay, so our equation was this. So A is equal to 2s divided by t squared. So we're going to have to combine uncertainties here. Ooh, okay. So first of all, we need to know the percentage uncertainty in S. And so that's going to be, what did the teacher say? 2 mil divided by, was it 170 mil? Yeah, that's what it was, times by 100. So basically 200 divided by 170, and that gives us 1.18%. And so we don't care about the 2 because that's just a number. So there is 1.18% uncertainty in that. There is 0.46% uncertainty in t, but it's t squared, so we double it. And then we're just going to add all these up. So therefore, total uncertainty is equal to 1.18 plus 2 lots of 0.46. I should be able to do that in my head, but not today, guys. And it gives me 2.1%. So that's what I think the uncertainty is. So don't forget that we only ever add up percentage uncertainties. We don't square them, whatever. We have doubled it here, but that's just adding up 2 lots of it. You know what I mean? 1.7, we have trolley diagram, reaction, weight, mass on a slope. Oh, I do love a good mass on a slope. And there's the weight, and there's the reaction. So reaction, weight. Resultant force, of course, is a result of both of these forces. It can be shown that G is equal to A divided by sine theta. We know this. Student determines G using this equation. State and explain how the student's value of G compares with 9.81. What? It's going to be less, as it is only the component of weight parallel to ramp that accelerates it. Or we could say, well, there is an upwards component to the reaction force, which means that obviously, therefore, the vertical force, the resultant vertical force, you might say, isn't going to be the weight. What a weird question. Literally, the mark scheme just says it's going to be lower, it's going to be less. That's all. What? That is the dumbest question I've seen in a long time, since paper 1 anyway. Okay, the Brinell test determines the hardness of a material. All right, so we have a steel sphere, Brinell hardness. Never heard of this, but that's to be expected. The unit of B, whatever. Okay, using this in... This is going to be a graph question, I can tell. Yeah, there it is. F was constant. D was 10 mil. And now we have a graph of B against H. Why have they done B against H? It should be B against 1 over H, as you can see from the equation. So we've got this shape here. B is there. Why is it in millimeters squared? Oh, okay, they're both in millimeters. That's fine. All right, determine the value of F that was used to produce figure 9. So, well, when are we going to have to get a gradient? No, I don't think so. I think we just need to get a value, don't we? Let's pick a value, one that's on a nice line. I'm going to pick, let's go with the bottom one down here. So B is, what's that? 30, no, it's just 30 kilograms per millimeter squared, and H is 3.1. I think it's close. Oh, I don't know. Is it halfway between? I'm not going to go to that accuracy. I don't think it matters. So I'm going to say 3.15 mil. We're just being asked to find F. That's all. Cool. So just rearrange the equation. F is just equal to, well, all of this nonsense multiplied together. So that's 30 times pi times 9.8. I'm not going to go with 9.81, guys. Doesn't make a difference. Times by 10 mil times by 3.15 mil. Now, we don't need to convert to meters because all of our measurements are in millimeters, so it all comes out in the wash. So what does this give us? I wonder. Let's go to 3 sig figs probably, because that could probably be that. So I'm going to say that is 29,100 newtons. 2.2, brass was not tested. When brass was tested using these values of F and D. Oh man, okay, so F is 29,100. What else did we know? D was 10 mil. And now we have H is 1.6 mil. And we're just being asked to find B. What is this? We're just rearranging equations. This is weird. Very easy so far. This is weird, guys. I feel like I'm being baited. 10 times 1.6. Boop, boop. Oh, I did use 9.01 there. Whatever. And I end up with 59. Yeah, the mark scheme says you could do a smooth curve and then just read it off. Yeah, okay, I guess you could do that, couldn't you? Yeah, you could just read off the graph. Whatever, either way is fine. This paper's weird, guys. B for leads is about 5 kilograms per millimeter squared. Show that this result cannot be obtained with the sphere. Show that this cannot be obtained with the steel sphere. Why can't that happen, guys? So let's get the equation again. So B is equal to F over pi GdH. So let's rearrange this. Let's find out. We know what B it is. We're trying to find H. So H is equal to F over pi GdB. And that gives us 18.9 millimeters. Oh, I get it. The ball is only 10 millimeters. So we'd need the material to be like that, wouldn't we? And so the ball would end up down here. That's not going to be helpful. Ball would be completely inside material into the lead. Oh, okay, figure 9. Right. So it's all about the graph. Graph H only to 3.5 millimeters. That's all you have to write there for H too large. To fix this, what would we have to do? Well, we could increase diameter of ball. Yeah, or of course we could reduce the force so it doesn't go in quite as far. Ooh, weird question. Oh, we're still going. Suggest a suitable instrument that can be used to measure this value of D. Oh, diameter. Oh, well, we use a micrometer for that, don't we? We wouldn't use a vernier caliper for that, of course, because, well, I mean, they don't play well with spheres anyway, because they just slip, don't they? Whereas with a micrometer, you've actually got 2 flat bits on the anvil, as it were, so it doesn't slip off the ball. Okay, for the indentation, so we have diameter is 7.33 mil, and H is 1.6 mil. Explain one advantage of finding B by measuring D rather than H. Well, oh, it's 7.3, right? And so, do you remember that? Oh, okay. So we're just comparing D and H basically. So D is larger than H. Therefore, well, if you have larger measurements, then by definition, it means that the uncertainty will be less. Therefore, percentage uncertainty is less. Therefore, more accurate. There we go. Okay, this looks like some Young's modulus. So we have density of steel. I'm just going to put, oh no, let's keep it in standard form for now. The total mass of both cables is 3.7 times 10 to the 4 kilograms, and we have a cross-sectional area of 9.6 times 10 to the minus 3 meters squared. Okay, we're calculating L. Let's just write down what we know density is. First of all, density is equal to mass divided by volume. And so that's equal to mass divided by cross-sectional area times the length. So therefore, all we have to do is swap over these two. So therefore, swapping over density, that is, I haven't done a very good job there. Length is equal to mass divided by rho A. Let's put it that way. And so that's going to be 3. Well, should we divide it by 2 or just times by? It doesn't really matter, does it? Let's go with halving it. So I'm going to say No, I'm not actually. That's well. Let's just divide by 2 in the equation because it's 2 cables. So I'm just going to divide by 2 there already, and then we multiply by the density there on the bottom, and then by the cross-sectional area. It seems like some powers of 10 are going to cancel each other out quite nicely. That gives me 260 meters. 3.2. The load is accelerated. The mass of the load. Oh no, are we going to have to add on the mass of the cables as well? I think we are. Oh boy, I think this is where the rubber hits the road, guys. Paper's been weirdly easy up until this point. I'm just going to say F, that's the tension, is 1.6 times 10 to the 6 newtons. That's just for one cable, and so therefore that's equal to 3.2 times 10 to the 6 for 2. So we're going to need that, of course. So if we want the total mass, first of all, let's do that. So mass total is equal to 2.8 times 10 to the 5 plus, what do we say, the mass of the, I think 3.7 times 10 to the 4. So that is, let's say 0. Let's just say that, let's say 0.37 times 10 to the 5. So that gives us 3.17 times 10 to the 5 kilograms. Okay, so we have our total mass. That is important. It's not often we have to take into account the mass of the cables, to be honest. So we have our force and we have our mass. We're trying to find the acceleration. But it's not as easy as just saying F equals ma because, of course, weight is involved as well. So there's a couple of ways of thinking about this, but we have tension going up there. We have weight pulling down here. In fact, we're not even told whether it's accelerating upwards or downwards. So, well, the way I think about it is this. How much force or tension, whatever, to hold. And, of course, if you're just holding something, then you're supplying a force that is equal to the weight, isn't it? And so that's equal to mg. So what is the weight, first of all? Well, that is the 3.17 times 10 to the 5 times by, I mean, all of this is a little bit moot because, you know, it's just pluses and minuses. And if we end up with a minus, then we've just assumed that it's going in the wrong direction. So, you know, but this is worth explaining. And so that gives us, the heck is that? 3.11 times 10 to the 6 newtons. Okay, so the force is greater than that. So actually, it is accelerating upwards. Greater, therefore, accelerating up. Not that important. Like I said, we're just looking for the magnitude of the acceleration. So it all comes out in the wash in the end, but whatever. So again, there's two ways of thinking about it. If you go down my route here, then we would say, right, how much force is needed to hold is equal to mg, but in order to accelerate upwards, we need to add on F equals ma as well. And so therefore the force is going to be mg plus ma. The other way of looking at it is, yes, F is equal to ma, but this here is the resultant force. And so what is the resultant force according to what we have on our diagram? Well, that's T minus W, and that's equal to ma. You'll end up with exactly the same answer at the end, exactly the same workings at the end. It's just coming at it from two different ways. I'm going to go with my way here because, of course, well, we're just using the values that we have. So I'm going to factorize this. So m, that's g plus a. And so therefore, f over m is equal to g plus a. And so therefore, a is equal to f over m minus g. So that's going to be our force of 3.2 times 10 to the 6 divided by the mass of 2.17. This looks like it's going to be around 10. Powers of 10. So that's just going to be 32 on top. And then take away 9.81. Yeah, so it's going to be a very small number, it seems. And so I end up with 0.28 meters per second squared. Not a super easy question there. For starters, it didn't tell you explicitly that you have to add on the mass of the cables. And if I'm being completely honest, I forgot to do that to begin with as well. 3.3, for safety, we have the braking stress is, let's put that in standard form, 8.90 times 10 to the 678 pascals. Deduce whether this system operates safely. That's nice and easy. So stress, we know, is just force divided by area. It's the same thing as pressure. And so we're talking about that force of 3.2. No, let's just go with one cable. So 1.6 times 10 to the 6 newtons divided by the cross-sectional area of one of these. What was that? 9.6 times 10 to the minus 3. Why not? Let's tidy up some powers of 10. Add 3 onto the top. I mean, you would hope that it's operating safely, wouldn't you? So 1.7 times 10 to the 8 pascals. So it looks like we're all good. You could, of course, calculate the force instead from the stress and then compare that with the tension that we're using. Okay, we have this. What is this graph? When the power demand is greater than the output of the wind turbine, the load and storage. I have no idea what's going on. Okay, the efficiency of the energy transfer. Oh my days. Efficiency of storage system to village equals, I'm just going to say that's 0.85. The maximum energy stored by the storage system is, I'm going to put that in standard form, so 7.6 times 10 to the 8 joules. Okay. Deduce whether the storage system, how did this question start off about lifts and then we're now talking about plumbing villages? Deduce whether the storage system and the wind turbine together provide all the electrical needs from the village from, what is this? 10 a.m. to 1400 hours. Okay, so looking at the graph. Okay, so after 10 o'clock, turbine too low. So of course we need the thingy. We need the storage system. I see. I think we might have to count squares, guys, because we have energy stored. And yeah, I think we're going to have to. Oh boy. Bois bach, as we would say in Wales. Bois bach, as we would say in Wales. So 10 o'clock to 2 o'clock. Okay, so that's not too bad. That's not too bad. So I think I can do that in a triangle and a trapezium. So I'm going to say, well, there's our dotted line, isn't it? And then boop. And then boop. And then it's going to be that in it. Oh no, I've messed that up, haven't I? So there's the shape of our little patch there. I'm going to split it up into a triangle and a trapezium like that. So I'm going to say that is, we're going to stick with hours for now. So we're going to end up with kilowatt hours. We'll deal with that in a minute. Well, that is 4 hours there. So we're going to say that's 4 times 50 divided by 2. So this just ends up being 100 kilowatt hours. And then this here, this trapezium, that's 4 and 2. Yes, so 3. This is the trapezium, so, whatever, 4 plus 2 divided by 2 times by, again, that's 50 as well. Is there an easier way I could have done this? So therefore, adding these up together, it seems like we need 250 kilowatt hours. Okay, kilowatt hours, of course, is power times time, so that is a unit for energy. We need to turn that into joules. So therefore, 250 kilowatt hours, let's turn that into watt hours. So that's 2, so we need to multiply by 1,000, don't we? So that's going to be 2.5 times 10 to the 5 watt hours. But then we need to turn that into watt seconds. And we do that, of course, by multiplying by 3,600. What do you know? That gives us exactly 9 times 10 to the 8 watt seconds. And of course, that is the same thing as joules. Watt seconds are joules. Okay, so, right. So we're looking at fairly similar numbers. So, well, I don't think it can do it then, because the demand is already higher, even when we don't take into account the efficiency. Let's take into account the efficiency anyway. So 7.6 times 10 to the 8, but only 85% of that can be supplied. So it's a little bit moot. You would have thought that they would have done the calculations such that if you didn't take into account the efficiency, then you'd end up with the wrong answer. But whatever. So we're going to say that that is 6.46 times 10 to the 8 joules. So therefore, 9 times 10 to the 8 is greater than 6.46 times 10 to the 8 joules, therefore demand greater than supply. And the reason this whole thing works, of course, is because we're just finding the difference between demand and supply from turbine. So basically, that difference has to be made up by the storage. So that's why this works. Not an easy question though, guys. Okay, bit of waves. Hopefully this will be nice and predictable. Oh gosh, maybe not. Two thin glass plates are separated by foil. Monochromatic light. Okay, so we got interference. A series of bright fringes is observed when viewed from above. Really? Oh, that's weird. Okay, well, of course, that's going to be because it's interfering when it reflects off. Yes, there we go. Looking at figure 15 here. Okay, the angle's very small, so we're just going to pretend that it doesn't exist. So everything's just flat. So fair enough. That makes things a little bit easier. At O, there is a phase difference between the reflected light from A and the reflected light from O. That makes sense. Phase difference is caused by the path difference due to the air gap and the refraction at A. What refraction at what? Oh, the reflection at A, right. At A, the phase difference of light that is reflected is changed by 180 degrees. So let's draw what's going on here. So I think this is actually more complicated than it first appears. It's because we have the light coming down, yeah, but when it goes from here down to here, but then it reflects back. Okay, so that's O, that's A. But at A, it says that the reflection results in a phase change of 180 degrees. So actually, wave is flipped here. Oh, okay, right. And then it's arriving in phase. And why do we know it's arriving in phase with A that's going down? Well, it's because constructive interference is happening. So this flipping of the wave, that's what's messing us up here. That's, as it were, adding half a wavelength. It's not a path difference, but, you know, it's doing the same job as adding half a wavelength of path difference. And so if it's arriving in phase, then that must mean that, therefore, path difference is equal to half a wavelength. Yeah, it could also be or 1.5 or 5 halves, etc. So it needs to be an odd one, and then we're adding on that extra half due to the flipping of the wave. Okay. So therefore, if the path difference is half a wavelength, then that must mean that D is equal to 1/4 of a wavelength. That makes sense, doesn't it? Yeah. We could give the, you know, quite often we give the relationship we're just talking about. It could be any n as well. And so if the path difference is all of these together, these would be, so path diff is equal to, what's that? That's going to be n plus half, and then that's times by that. Whew. And so therefore, we could say then, well, that's actually going to be that instead. So D is equal to half that. Right, there we go. Not an easy question, that one. Okay, it can be shown that T over L is equal to lambda over 2S. All right. And we're going to have to count some fringes here, methinks. Yep. So lambda is equal to, I'm going to say that's 5.9 times 10 to the minus 7 meters. L is 6 centimeters, so I'm going to say that's 0.06 meters. And then, of course, we're looking for T, so therefore we need S. S is equal to, well, it's 5 millimeters. 5 times 10 to the minus 3 meters divided by, how many fringes do we have? Remember, we start with 0, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 fringes, so that's what we have. Do you know what? I'm just going to leave that as that and then pop that back into here, methinks. So therefore, T is equal to lambda L divided by 2S. So that's going to be our 5.9 times 10 to the minus 7 times by 0.06 divided by 2 times that 5 times 10 to the minus 3 divided by 11, but because we're divided by 11, I'm just going to put that on top there. 2 times 5, that's just going to be 10. 10 times 10 to the minus 3. So that is just 1 times 10 to the minus 2. So adding that onto the top here, that ends up being minus 5. We can actually get rid of that there. And I end up with 3.89 times 10 to the minus 5 meters. Our data was 2 sig figs. Minimum accuracy, so I'm going to say that's 3.9 times 10 to the minus 5 meters. Whew. Nearly done with section A, guys. Space between the plates is now filled with water. Same light is used. Deduce how the distance S will change when water fills the space between plates. Okay, so refractive index of water is 1.3. That, of course, tells you how much slower light travels in the medium. So therefore, I'm going to say the speed of light in water is going to be 3 times 10 to the... Am I going to use this? We'll see. I'm just going to leave it as that for now, divided by 1.3. Getting our T divided by L equals lambda over 2S. Okay, so if it's refracting in the water, so refraction C, well, you know, if it's in water, C gets less, F stays the same, and lambda decreases as well. The waves bunch up, don't they? Of course, C goes down by a factor of 1.3, and so therefore that happens to the wavelength as well. So looking at our equation, T is the same, L is the same. So what's the relationship between lambda and S? Well, if we move S to the other side, we can see that S is proportional to lambda. So therefore, if lambda divides by 1.3, so does S. There we go. Easy peasy. Yeah, weird question. Finally, multiple choice. Save us, please. Question 5. Nuclide P ends with an isotope of P. What is the possible sequence for these decays? Okay, so in order to be an isotope of P, we need same protons at end. Number of protons at end. No, not hashtag, you zoomers. So alpha decay plus 4 beta decays. Well, no, because that's going to result in minus 2 protons and then plus 4. So that's not right. B, looks about right, doesn't it? Alpha and 2 beta minus. So that's minus 2 plus 2 because, of course, neutrons turn into protons. So I think the answer is going to be B. 6, current is 0.33 amps. How many electrons pass a point? Okay, units are your friends in these kind of situations, guys. So we have a time of 7 minutes. So that's going to be times by 60. That's 420 seconds. And electrons per second. Okay, let's write down what the charge of an electron is first. So that's 1.6 times 10 to the minus 19. But I'm just going to say that's coulombs per electron. And we want electrons, but we have electrons to the minus 1 here. So we know we're going to divide by this in a minute. So we have coulombs per electron. What is amps the same as? That's the same as coulombs per second. So therefore, if we take our 0.33 coulombs per second, divide by 1.6 times 10 to the minus 19 coulombs per electron, then hopefully you can see that coulombs cancel. Electrons will end up on top, and we end up with electrons per second. And then, of course, we can find that number, then multiply by 420. But let's do that anyway. Times by 420, seconds disappear, we're just left with electrons at the end. So let's pop that in, and I end up with 8.66 times 10 to the 20 electrons passing in 7 minutes. So it seems the answer is C. Question 7, we have monochromatic light, and we have a diffraction grating. So we have the wavelength is 520 nanometers. Tell you what, I'm going to leave it like that for now, and we have n equals 3. So I'm going to write down the diffraction grating equation. We're told the angle is the same and d is the same. So therefore, if we make a proportionality equation, we can see that n is inversely proportional to lambda, or we could just say n lambda is equal to a constant. So that means we can say n1 lambda 1 is equal to n2 lambda 2 afterwards. So actually, because of proportionality, I don't think we need to turn this into meters at all. So we're looking for lambda 2. So let's just rearrange that. So lambda 2 is equal to n1 lambda 1 over N2. Of course, we can split that up into just N1 over N2. And so this just ends up being 3 over 4, so 3 quarters, times 520. So I think that's going to give us 390 nanometers. So I think the answer is B. No calculator needed. Question 8. Alpha particle, positron, proton have different... Blah, blah, blah. Which row shows the particles have the greatest and smallest value of this ratio? Ugh. Okay, so alpha is... Well, we know that... Okay, so charge to mass ratio is just Q divided by M. So let's go for this. So alpha... There was a question like this in 2023, if I'm not mistaken, actually, as well. So we've got an alpha particle. So the charge of that is going to be 2. And the mass of that is going to be huge. A positron... That's going to be just 1, charge of 1, divided by a mass of tiny. And then a proton is going to be 1 divided by a quarter of huge. So, of course, because a positron has such a tiny mass, this is going to have the greatest value of charge to mass ratio. What has the lowest ratio for the alpha and the proton? Well, of course, we have just, we can just say a quarter. That's just going to be 1, as it were, forgetting about this for now. And then, of course, that's 2 divided by 4, isn't it? Because it's 4 nucleons, whereas a proton is just 1 nucleon. So this is going to be 1. This is going to be a half. So therefore, alpha is going to be the lowest or smallest. So I think the answer is going to be A. 9, we have this circuit and we have a voltmeter across the resistor. Yes, I could draw straight lines, but I don't have time for that. And that's 12 volts. To begin with, LDR has a resistance of 480 ohms. And so the voltmeter is 2 volts reading. And so therefore, if we know that's the case, then we know that this is 10 volts. And then the LDR is 8 volts. No, sorry. The voltmeter is reading 8 volts. So therefore, this must be 4 volts now. And so therefore, what has happened to the resistance? Let's figure out what the resistance of this resistor is, shall we? And so therefore, well, we can see that we could go talk about ratios and stuff like that, but we can see that the PD is 5 times less for it. So therefore, the resistance to begin with is going to be 5 times less as well. So that's 96 ohms. And then afterwards, well, we just need to do the opposite then. This stays the same, of course, because it's a fixed resistor. And then we just want to find that. And so therefore, well, it's 96 ohms, but we can see that this is 2 times less. So therefore, the resistance is going to be 2 times less as well. So that is going to be 48 ohms. So the answer is A. 10. Okay, energy in a spring. We know that energy is equal to half F delta L. Now we can't use this because, well, both of these are changing. So we can't say E is proportional to F, E is proportional to L. So of course we substitute in Hooke's law into that and we end up with E is equal to half K delta L squared. And we can do the opposite as well. We can say that delta L is equal to F over K. So we can also say it's equal to half F squared over K. So therefore, E is proportional to delta L squared, because K and half are constant, and E is proportional to F squared too. So actually, it's going to be a curved line for both. So it's D. 11, we have a graph of something falling. Okay, so Y and time, and it's doing that. So which row gives Y and the amount of air resistance? Right. Okay, so if it's A, if this is distance here, well, it's not going to be distance, is it? Because that implies that the distance is not getting any greater. So it's actually stationary at this point. And so therefore, it's going to be 0 then, isn't it? It's not going to be distance, let's be honest, because we're talking about speed and how it changes there. So let's go for V instead. Yeah, of course, it's not going to be negligible, because of course, it's not stationary anymore. It's a constant speed. So if it's a constant speed, then therefore we've reached terminal velocity. So that must mean there must be air resistance. So the answer has to be D. What a weird question. And by weird, I mean crap. Electric pump forces water. This is, no, I don't know actually. So V is 4 meters per second. Cross-sectional area is 5 times 10 to the minus 4 meters squared. And, I've forgotten the density of water, of course, is 1000. What is the useful power of the pump? So we're looking for power. Now, my first instinct was to go for, well, F equals rho A V squared, because more often than not, when we see a fluid in a pipe that's moving, we're asked to find momentum carried per second, and that gives us the force. And then I thought I could just do P equals FV, but you can't do that. The reason this doesn't work is technically this, well, that would be if we're accelerating the fluid from rest, or if it's smacked into a wall, it would lose that momentum per second as well. Problem is, we don't really know what's going on before the pump. Is the water going in at 2 meters per second? We don't know. And so all we know is that the fluid is moving at 4 meters per second when it comes out of the pump. And so that's why we must use, just our normal power equation, P equals E over T. And of course, what kind of energy is it gaining? Well, it's going to be kinetic energy, so that's half mv squared. So power is going to be that divided by T. Well, we have V, we don't have M, we don't have T, but if we do M over T, similar to our whole rho AV squared derivation, if you don't know that, have a look at my momentum video, then we end up with, well, that would be half times, this would be the density times the volume divided by time. That is the flow rate, meters cubed per second, times by speed squared. And once again, we don't have volume, but we can split that up into rho A L over T, and then times by V squared there. And then finally we have L over T there. So this doesn't end up being rho AV squared, but it ends up being half rho AV squared, then times that extra V. So this is half rho AV cubed. So that's a half times 1000 essentially, times by 5 times 10 to the minus 4, times by 4 cubed. And that ends up being 16 watts. That is not a nice question. 13, current of 4 amps, power of 8 watts. What's the PD when the power is 32 watts? Okay, so it's a resistor, so therefore we're just going to say P equals I squared R. So therefore resistance is equal to P over I squared. So that is 8 divided by 4 squared, and that gives us, well, it's 8 divided by 16, so 0.5 ohms. Okay, and then afterwards, so, well, P is equal to V squared over R, because we want the PD this time. So V is equal to the square root of RP, fail RP. So that is going to be 0.5 times 32. So this is the square root of 16. So that is going to be 4 volts. So I think the answer is B. 14, monochromatic, blah, 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 blah. When monochromatic radiation from light source Q is used, no photoelectrons are emitted. Which property must be greater from P, must be greater than that from Q? It's going to be frequency, isn't it? Because we know that EK is equal to HF minus phi. We know threshold frequency. It's, if the frequency isn't high enough, then of course, you know, we have the graph, don't we? So therefore, you know, P is going to be here. Q is going to be down here or whatever. Frequency is not high enough for Q. Question 15. All right, so we're moving this thingy away from here. This is 1 meter. The wavelength is 5 centimeters. So I'm going to say that that is 0.05 meters. And so therefore, well, we need the distance here then. If it's 1 meter, then the next maximum is going to be when this path difference, so it's going extra, isn't it? So when this path difference is 0.05 meters, and so therefore this whole length is going to be 1.05 meters. So therefore, reverse Pythagorasing this bad boy, we can see that this distance here is going to be equal to 1.05 squared, take away 1 squared, and that gives us 0.32 meters, so 32 centimeters. So I think the answer is D. 16, quark structure of K plus meson. Well, we know kaons must have strangeness, and a strange quark is similar to a down quark insofar that its charge is minus a third. So therefore we want an anti-strange quark, because that's going to be plus a third. So therefore we know it has to have a strange quark. In order to be plus altogether, we must have an up quark in there as well. So it looks like it's going to be a... Oh my days, are you kidding me? Are you kidding me? The question doesn't say K plus meson. I wasn't reading it properly. In fact, the microphone was covering that bit of the question. That's my excuse anyway. The question says the quark structure of the antiparticle of the K plus meson. So we're actually looking for K minus. Are you flipping kidding me, AQA? And if you look at the examiner's report, they're like, most people said up anti-strange. This is the K plus meson. Oopsie. 17. What is the de Broglie wavelength of a positron? Okay, so lambda equals h over mv. And so therefore we're going to say that that is Planck's constant divided by the mass of a positron, which is the same thing as the mass of a proton. I think we can cancel some powers of 10. And then 5% of the speed of light. So therefore we're going to say times by 3 times 10 to the 8 times by 0.05. Let's add that onto there, so minus 11. And that gives me 4.9 times 10 to the minus 11 meters. So I think the answer is D. Okay, we have this, 3 resistors. Okay, what is the power in X divided by the power in Y? Right, so power is ultimately to do with, well, in this case, PD. So P equals V squared over R. That's what we're interested in. And they are identical, so therefore we can say that P is proportional to V squared. So if this is, say, 2 volts across here, what's it going to be across the parallel resistors? It's going to be 1 volt. Why? Well, it's because they have half the resistance altogether, and because they're in series with the other resistor, half the resistance, therefore they're going to get half of the PD. So therefore we can say that that is the same thing as the ratio of the PDs. And like I always say, when you have questions that say, what is this ratio of this to this? You're always looking to replace or substitute in what those things are proportional to. In this case, proportional to V squared. So it's going to be 2 squared divided by 1, so it's going to be 4. 19, we have a graph of acceleration against time. So we're told that at time 0, V is 4 meters per second. We're asked for the final speed here. But we have an acceleration time graph. We very rarely deal with acceleration time graphs. But just remember that when we have a speed time graph, the area under the graph gives us the distance. We're going down. This is a little bit of calculus, actually, differentiation, integration. We are essentially integrating here. Does it stand to reason then that if we have an acceleration time graph, the area under the graph will give us the increase in speed? Well, yes, it does work like that. So we can say the area is equal to 2 is a trapezium, so 2 plus 6 divided by 2, that's just going to be 4 in it, times by 5, so that's going to be 4 times 5, that's going to be 20. So therefore, final velocity is going to be equal to 20, it's going to be equal to 4, the initial 4 plus 20, so that's just going to be 24 meters per second. Object is released from rest, air resistance, whatever. After falling for time t, the momentum of the object is... Oh, okay. Right, momentum. P is momentum, and so that's equal to mv, and so therefore P is proportional to V. So therefore we want to know what is happening to V. Ultimately, they're asking us about momentum, but actually it's about velocity, isn't it? So let's go with an equation that has V in. So V equals U plus AT. U is 0. Acceleration is going to be constant because air resistance is negligible. Therefore, V is proportional to T. Therefore, P is also proportional to T. Therefore, our answer is C. 21. Cladding of a step index optical fiber. Transparent. No, it must not be transparent. No, that's a lie. It can be transparent so long as it's the right... refractive index, that's fine. Must have a higher refractive index than a core. Nope. It must have lower in order for TIR to occur. C, reduces signal loss. Yes, it does, because it means that the light doesn't go into the protective sheath. D, reduces material dispersion. No, it doesn't. Doesn't affect. Or does it? No, because material dispersion is just to do with the core. So answer C. 22, cricket ball. U1, no, just U. that's fine. 35 meters per second. Contact time is 52 milliseconds, so that many seconds. And then V afterwards is minus 30 meters per second. That's the thing that we have to remember. What's the average force on the bat or the ball, whatever, it doesn't matter, same thing. So F is equal to rate of change of momentum. And so that is the same thing here as mass times acceleration. There's a couple of ways of thinking about it, of course. It's exactly the same thing in the end. So we just take the mass times by, well, that's 35, take away minus 30, because that's what you got to be careful of, and I guarantee that's where most people would have got this wrong. I'm not saying most people got it wrong, but if you got it wrong, that's why you would have ended up with 5 over 0.052, but no, it ends up being 65, doesn't it? And we end up with bang on 200 newtons. So our answer is D. Oh, horse is walking. This is a maths question. This isn't a physics question, whatever. Circular track of circumference 60 meters. So speed is 2 meters per second. Oh, the horse's displacement. Right, okay. So after 45 seconds, so distance is speed times time. So that is 2 times 45. So that is 90 meters. And so therefore, the horsey has gone round and then there. So 1.5 rotations. So it's ended up completely the opposite. So therefore, displacement is going to be equal to the diameter. And so therefore, we need to calculate that then, don't we? So circumference is 2 pi r or pi d. So that's equal to 60 meters. So therefore, the diameter is equal to 60 divided by pi. And I don't think we need to calculate for this. I know it's going to be below 20 because it's divided by 3 point something. So it's going to be less than 20. So I think the answer is probably going to be 19. 24, which statement is true? A brittle fracture occurs after little or no elastic deformation. No, because if we have the graph of, force against extension, whatever, or stress against strain, if it's brittle, it can do this. So actually there can be quite a bit of elastic deformation, but then it just breaks all of a sudden. So that's the brittle part. So it's not going to be that. B, no plastic deformation. Yes, that's our answer, isn't it? Because there's not going to be a plastic region for something that is brittle. It's not ductile. Let's just check the other one. C, plastic deformation energy is stored in proportional to stress. No, because of course it's past the limit of proportionality. And D, stress is proportional to strain. Same thing. So it can't be D either. 25, we have masses. Tension in X is 319. What's the tension in Y? Okay. This should be fairly easy. So all we have to do is resolve horizontally, methinks, because we know it's not going anywhere. We know that the horizontal components of both of these forces must be the same. So what we can say is that force in X times cos 12, multiplying by cos because we're turning through the angle, and we're multiplying, not dividing, because we want a smaller number. That's going to be equal to Fy cos 34. So therefore, all we have to do, divide by cos 34 there, which is equal to 390 times by cos 12 divided by cos 34. And I get 460 newtons. So I think the answer is D. And like I said, that's because these have to be the same, the horizontal components. 26, maybe I should draw straight lines. Oh, said they'd be straight, didn't say what angle they'd be though. Oh, dearie me. So we're putting a voltmeter across there. I am not going straight lines with that. So 5 centimeters, 15 centimeters, and 5 centimeters. Oh, this is really easy, guys. Come on. Look, it's across 3/5 of the thingy, isn't it? So it's going to be 3.6 volts. That's crazy. That's super easy. 27, we're lifting at a constant speed. That's okay. Distance of 3 meters in 1.5 seconds. Oh man, why do they make this complicated? So V is just 3 divided by 1.5. So that is 2 meters per second. So we have the speed. The load, which is the force, is going to be the same as the weight because, of course, it's supplying the same force as the weight. So force is going to be 750 newtons. What is the efficiency of the lift? Okay, so P equals FV. So that's just going to be 2 times 750. So that's 1,500 watts. That is useful. And then we need to switch tack to look at the motor. So P in this case is VI or IV. And so that's going to be 12 times 200. So that's going to be 2,400. So therefore, efficiency is just going to be 1,500 divided by 2,400. Powers of 10 cancel. So, and then it's going to be times 100. And that gives us 63%. Okay, wire, we have a length of 0.12 meters. And we have resistivity of 2.7 times 10 to the minus 8. Oh, and I missed the volume. Okay, so we want the resistance, so let's crack out our resistivity equation. Now we could find the area from the volume and length, but there is a bit of a shortcut here, and then of course is that area is equal to volume divided by length. So why don't we just pop that in there instead? So actually we end up with rho L over V over L, and so that L ends up on top, so it's just rho L squared divided by the volume. So let's do that, why not? I'm going to tidy up powers of 10, and I get 1.1 times 10 to the minus 6. So I think the answer is A. 29, glider, mass. Okay, so this is momentum. So mx is 400 grams. I don't think we need to convert that because it all comes out in the wash in the end. My is 300 grams. And ux is... to the right, so I'm going to say that's positive 1.8 meters per second, and then y travels to x. Okay, so we could just go in the other way. So uy is minus 0.7 meters per second. Okay, they collide, and so we have vy is now equal to 0.9 meters per second. We want the speed afterwards for x. Nice and easy. So all we have to do is say mxux plus myuy equals mxvx plus myvy, and just be really careful with our pluses and minuses. That is it. We don't need to convert. We could actually just call that 3 and 4 actually, because it'll, like I said, come out in the wash. So I'm just going to very quickly just take this over the other side. That's the myvy, and that's equal to mxvx, but then I just need to divide by mx, so I'm just going to take that over there. That wasn't very straight, and there we go. And actually there is one more shortcut I could do, and that is just get rid of that there and just have ux by itself. And you know what? I'm going to factorize it as well. I'm just going to then do that. Of course, you can put the numbers in first if you want to, up to you. So I'm just going to say that's 1.8 plus, so that's 3 times uy, so that's minus 0.7 minus 0.9. Divide that by just that 4. There we go. So that should equal our answer. So what's that going to be? And I end up with 0.65 meters per second. It's not a negative, it's a positive. So I think it's to the right as well. So I think the answer is A. I flipping hope it's A anyway. Yep. 30, stationary wave, superposition, both the progressive, polarized. Which statement about the progressive wave and its reflection is true at an antinode? A, they must be longitudinal waves. No, they could be transverse. Well, actually, they can't be longitudinal because longitudinal waves can't be polarized by definition. B, they must be coherent. No, coherent means that the phase difference is constant. That's not the case for waves traveling in opposite directions. C, they must have different frequencies. Of course not. They must be the same frequency. D, they must be polarized in the same plane. Yes. Otherwise, they won't interact at all. 31, 3 non-parallel coplanar forces act on a body. So whatever. Which is not required for the forces. Okay. The sum of the forces in any direction must be 0. Yes. If we resolve and then add them up. So yes, technically. B, no moments. Weird way of putting it, but that's what it's saying. So yes. So it's not going to be our answer either. C, the lines of action of the forces must pass through the center of the mass of the body. No, that's not true at all, is it? Well, that does the opposite, because when that happens, there's no moment at all. So that's going to be our answer. D, the resultant of any two forces must be the same magnitude as the third force. Yes, that's similar to A, isn't it? We've resolved, and they're all balanced. 32. Which row is correct for progressive and stationary waves? Some of the particles do not vibrate. No, with a progressive wave, every part of the wave moves. That's the whole point. It's not a stationary wave. Stationary wave, all the particles vibrate in phase with each other. No, that's not true, because we know they can have the opposite phase if they're the other side of equilibrium. They're always 180 degrees out of phase with each other. Okay, B, none of the particles vibrate with the same amplitude. No, they do vibrate, so that's not our answer. They all have the same amplitude. All the particles vibrate with the same amplitude. No, that's not true either. So it's actually the opposite. C, in fact, it doesn't need to be true for progressive wave, whatever. We generally say that. C, all the particles vibrate. Yes. And then progressive wave, some of the particles do not vibrate. Yes. So C has to be our answer. There we go. Let's just check D real quick. All of the particles vibrate in phase with each other. No, because different points on the wave are out of phase with other points. None of the particles vibrate in phase with each other. Yeah, they do, because, with a stationary wave, every particle above equilibrium is in phase with its neighbor. They're just out of phase with the ones the other side of equilibrium, 180 degrees out of phase, like I said. 33. Student investigates characteristics of a power supply. Okay, so we have, whatever. PD on the y-axis, current on the x-axis. Which feature of the graph represents the EMF? Come on, guys. We know this. We know the graph is going to end up like that. And this is the EMF here. So it's going to be D. Finally, 34. Which row shows SI prefixes in order of increasing magnitude? Well, there we go. Nice and easy to finish off with. Let's check. A. Femto, yes. Pico, yes. Micro, yes. Centi. I was like, C? Yes, that's the largest. So A does look like that's our answer. That's nice. We don't even have to check the others. And of course, this is 10 to the minus 15, 10 to the minus 12, 10 to the minus 6, and 10 to the minus 2. So I hope you found that helpful. Gosh, this was a bit of a slog, this paper. Not as nice as paper 1, methinks. Multiple choice was pretty tricky, wasn't it? Leave a like and a comment if you did find it helpful, and I'll see you next time.